x is 0 at the highest weight vector. Everywhere else it's simply. So this is also an irreducible example. There are many indecomposables one can construct if your break set is non-empty. So these were examples of infinite orbit. Those are called linear orbits. Now, when the orbit is finite, these are called circular orbits. You again have two major cases. Orbit is finite, the breaks, there's no break. So this can be viewed as follows. This is circular orbit, for example again, fix an F. So here I am algebraically closed. If I'm algebraically closed, then one can show that every weight space is one-dimensional. Otherwise, you have more things. So you take a non-zero scalar, then you can view. So this is a circular orbit. So you can start at some position, say m0. X is t m0. I mean x y m0, and keep going. This is x until you come to a certain point, say mk, and here x is simply multiplication by r. It's circular. T goes back 1. T returns. So these also give you irreducible weight modules. And the last case is when you have finite orbit and breaks. There are two families. This is difficult to explain, so I'll just give you this is difficult to explain in the sense it's quite technical. The definition is quite technical. Since there are breaks, what I'll just give you the picture. X goes a certain direction and then gets a 0. There is a break. Y goes in the opposite direction and then, not Y, T goes a certain opposite direction and gets a 0. This is one option. This is an example. The other option is, even though there are breaks, so somewhere could be a 0, but that's okay. Keep going. At the last one, x comes back via multiplication. Wherever x is 0, t is 1. That keeps it indecomposable. And reverses arrows basically. So wherever x is 0, t is 1. Wherever t is 0, x is 1, to make sure everybody is indecomposable. So if you want, I'll send you the files with the precise definition. Let me know if you're interested. So anyway, this is the idea. So 1 hour gone. My motivation, algebra of quantum differential operators. So there is a certain algebra that I and McCune had defined. We called it algebra of quantum differential operators, polynomial ring, one variable. It is an algebra. So, okay, what is everything? So, K is a field over rationals. Q is some non-zero complex number. Q not a root of unity. Not a root of unity. Given this setup, McCune and I had constructed algebra of quantum differential operators. They contain 4 operators. One is multiplication, so let me write them all. Del x, del 1, del minus 1. For the usual while algebra, you just have x and del. For the quantum while algebra, you have x and del 1. Our algebra contains all these. So x does what x always does, multiplication. Del is the usual derivative. What does del 1 do? Del 1 on x raised to n. And what does del minus 1 do?
There's no x.
Oh, x raised to n minus 1. Okay. So, Jordan and I, we had studied this particular algebra. We have shown that this is left-right Noetherian. It is a simple domain, GK dimension 3. Now, with we were also able to come up with defining relations. Defining relations among these 4 generators. They are this is the while relation. You see, where usual derivative is viewed as del naught. No Q. Then del I x del j equals del j x del. So notice these del i's don't commute among each other. But if you interject an x, then it's okay. Then the last one, del minus 1 del. This is a quantum commutation.
The middle relation is no Q?
No.
Okay.
So they are almost commuting, but they don't really. You have to have an x for them to commute. So these are the defining relations, and that was a lot of work. Now it turns out this ring has
So how does the I range here?
and you see del 1, del minus 1.
Wow.
Del has to be viewed as del naught.
Oh, okay. All right. So 0, minus 1 and 1.
Correct. Oh, okay, yeah.
That's fine, that's fine.
So the following is joint work with Futoni. So notice dq, I'll shorten this, I'll call it dq. So dq is integer graded. You see? As operator, multiplication has degree 1 and all the derivations have degree -1, going in the opposite direction. So let R be the 0 degree part of dq. One can show R is a polynomial algebra, rather localization of a polynomial algebra. Where what is tau? Tau is the usual while tau.
Sigma.
And sigma is del 1 x minus x del 1. This is degree 0. Turns out this is invertible. It is inversely exactly what you would expect. Now viewed in this fashion, you have dq and you have r. This is commutative. So you can build GWA over this. Over this, I can put x, rather multiplication, and I can add del, or I can take multiplication and I can add del 1. You see? They are both, this is the Weil algebra over R, this is the quantum Weil algebra over R. You see? And dq contains both of these. Is this okay? So dq is 2 steps away.
I lost track of Q. What was Q?
Q was a non-zero scalar from your field.
Oh, okay.
Not a root of unity. So far all of this has been defined for a not root of unity. Q.
Okay. All right.
So for instance, Q shows up here, you see. Sigma of x raised to n is precisely q raised to n x raised to n.
Oh, okay.
That's right. So dq contains both the first Weil algebra over R and first quantum Weil algebra over R. Right? dq, so if I just view first Weil algebra over R, so this contains x and del, I just need one more generated. And vice versa. If I have del 1 here, I need del, that's all. So Futoni and I were able to,
So you're making this into a generalized Weil algebra?
it is not a generalized Weil algebra.
Oh.
It is an algebra over a generalized Weil algebra.
I see.
So we were able to extend almost all the indecomposables from here to here.
I see.
So that is my last result. Skipping a few pages. So, right. So what we are able to say is that one theorem for a talk. When you have an algebraically closed field, every irreducible d dq weight module. So weight module with respect to my localized polynomial ring is indecomposable. As an A1 and A2.
Okay.
Yeah.
Oh, as an, oh, I see, as an
A1.
oh, I see, yeah.
So the point is, so the indecomposables here have been described by Droz, Guzman, and Ovsienko. So if I want to study irreducible here, I just have to study indecomposables here and extend. Some of them extend, some don't.
So these indecomposable modules, they're not irreducible, I mean.
No. So irreducible means simple, has nothing smaller.
Oh.
Indecomposable means could have something smaller but doesn't split. Yeah. So yeah. And the next question was, what about indecomposable DQ modules? Turns out that is a wild problem. So that we. So okay. So I'll stop here.
I didn't get the last comment about your indecomposable.
Indecomposable DQ modules,
Yes.
Classifying that as a wild problem.
Oh, I see.
No, wild problem. We know it's a wild problem. Wild in the sense there are too many. It boils down to, for example, polynomial algebra in more than one variable. Classifying all of them, you can't. So yeah, credit goes to Fotoni.
So in these generalized algebra, you don't consider that much interaction between the operators, the alpha, the automorphism, let's say. Other than that, either they commute or they don't. Other than those relations.
I mean, I don't understand. So if you here, I mean, for example, you see, if your alpha is identity, then you construct while algebra.
Right.
Okay. If your alpha is alpha, so this is alpha on polynomial algebra one variable. If alpha x equals qx, then you get
A2, right.
A1q. That's right. Quantum while algebra. Now, if Q is a root of unity, this has finite dimensional modules, whereas while algebra never has finite dimensional modules. So, I mean, characteristic 0, right? So, they are not even Morita equivalent, you see. So, it does matter.
Is there a higher rank version of this?
Of DQ, yes, I have, so that's,
Yeah.
that's something I want to
You're
look at.
working on that? Or?
I haven't started, yeah.
Okay, yeah.
This one we barely submitted now recently.
Is there any version for, instead of automorphisms, uses endomorphisms?
Just endomorphisms or to construct generalized while algebra? Not to my knowledge, but Jordan has worked on, say, Ore extensions where they are not automorphisms, but monomorphisms.
One more.
Yeah.
So you use the theorem in the paper that you mentioned. They have a lot of typos. to do this?
Yes.
Okay.
Yes,
I
yes.
see. That's the tool.
That's the main, yes.
The typos are the main tool.
Yeah.
No, but they were helpful because I understood them
It's a nice
better,
project.
you know. I was not sure at all, how is this possible? And so it turned out they had many typos. Right in their main theorem, typo.
If
Oh, it's been.